This is a diagram that shows us essentially what the atom looks like. It's not quite our current model of the atom. The current model of the atom has what we call electron clouds, and it's hard to represent that in the picture, but this is more or less the structure of the atom that we currently accept. What is it that we have in the middle? What do we call that thing in the middle of the atom? No, that's okay, actually, because inside this thing, there are neutrons, yes?
Protons.
And there are protons. What do the protons and neutrons make up? The nucleus, right. The nucleus, which is the center of the atom consisting of protons and neutrons. What's the charge of a proton? Positive, right? And what's the charge of a neutron? No, it's no charge. Now, what do we have? These things that are orbiting around this nucleus here. Yeah. These electrons are negatively charged. Now, if we look at the charge, the proton and electron have the same charge but opposite. So if one is +1, the other is -1. The neutron is completely neutral. If we look at mass, it's completely different. The proton and the neutron have a similar mass. The neutron is ever so slightly heavier than the proton is. Not much, but if we go to the fourth significant digit, the proton is a little bit lighter than the neutron. For most intents and purposes, the neutron and proton have the same mass. The electron, on the other hand, has a mass that's way, way, way lower. In fact, the mass of an electron is like something like 1/1000th the mass of a proton or a neutron. So most of the mass of the atom is made up in the nucleus. That's the protons and neutrons. But the charge, hey, half the charge comes from the nucleus, which is the protons, and half the charge comes from these electrons that are orbiting around it. Most of this unit on electricity is going to be the study of these electrons. Electricity, electrons. They come from the same base word. Now, we want to talk about the types of charge here now. Not so much protons are positive and electrons are negative, but positively charged objects. Where do they come from? If I rub a balloon against my hair and it gains a certain charge, let's say it becomes negatively charged when I rub that balloon against my hair, what's the consistency of that balloon? What makes up that balloon? It's not just electrons. If it's negatively charged and it's not just electrons, then what makes it up? If something's positively charged because I rub it against something else, then what makes it up? We have to understand that everything has protons and every object has electrons and neutrons as well, but neutrons aren't particularly relevant to us here. If we have both protons and electrons, then something with a positive charge simply means that we have more protons than electrons. We're always going to have some of both, but we have more of one than the other, more protons than electrons in that case. If we have negative charge, then that simply means that we have more what? Electrons. Yeah, the electrons are negatively charged, so it means that we have more electrons than protons. And of course, if something's neutral, you can have a neutron that's neutral, just like you can have a proton that's positive and an electron that's negative. That's not what we're talking about here, okay? We're talking about a neutral object. The desk that you're sitting in is neutral. That desk has both protons and neutrons, and in fact, protons and electrons. And in fact, it has an equal number of protons and electrons if it's neutral. Now let's quantify charge. How much charge do we have? If I said how much speed do we have, you would say, when you're driving on the highway, maybe 100 kilometers per hour. If I said how much acceleration do you have when you're jumping off of the edge of a desk, you would say, it's 9.81 meters per second squared. We have a notion, an intuitive notion as to what a meter per second squared is or what a kilometer per hour is, right, from experience. We don't have a notion as to the unit for charge. The unit for charge, by the way, is a coulomb. But what does that mean? Like, how much is a coulomb? A coulomb is actually a really, really big unit of charge. In fact, it's so big that it takes about about that many electrons to make up a single coulomb of charge, or that many protons to make up a single coulomb of charge as well, since a proton and the electron have the same but opposite charge. You don't need to write that number down. Just know that a coulomb is a big unit of charge. A meter, standard unit for distance, okay? A light year is a massive unit for distance. A coulomb is the standard unit for charge, but it's also a massive number, a really, really big number. It takes a lot to get a full coulomb of charge, just like it takes a lot to get a full light year of distance. How much? Well, the charge of an electron is negative 1.60 times 10 to the minus 19 coulombs. Hence, it requires about 10 to the 19 electrons to get a coulomb of charge. Similarly, the charge of a proton is plus 1.60 times 10 to the minus 19 coulombs. Where do we find this number on our data sheet? If you have your data sheet handy, take it out and take a peek, but if you don't, just look up here. We see the charge and the mass of a bunch of particles, an alpha particle, which we saw once in Unit 1. Don't really know what it is, but the electron, the proton, the neutron, and then some first-generation fermions like a positron and a neutrino. We'll talk more about those in our last unit. The masses given to us in kilograms, easy to read, right? The mass of an alpha particle, 6.65 times 10 to the minus 27 kilograms. But what about the charge? It says the charge of an electron is minus 1e, and the charge of a proton is plus 1e. What does that mean? Like, we want coulombs, right? We want 1.6 times 10 to the minus 19 coulombs so that we remember what the charge is. How does that help us? Well, over here on the left-hand side of your data sheet, it says the elementary charge, that's the smallest possible charge that you can have, is 1.6 times 10 to the minus 19 coulombs. And the symbol for that is E. So if an electron is minus 1e, then the charge of an electron, by the way, the symbol for charge is Q. The charge of an electron would be minus 1 times 1.60 times 10 to the minus 19 coulombs, the elementary charge. That gives us a total charge of minus 1.6 times 10 to the minus 19 coulombs. The charge of a proton, QP, is plus 1e, which is plus 1 times 1.6 times 10 to the minus 19 coulombs, gives us a total charge of plus 1.60 times 10 to the minus 19 coulombs. You didn't need the charge of an alpha particle when you did that question back in Unit 1, but if you did, you'd look at this and say, oh, it's plus 2e, so it would be plus 2 times 1.6, or 3.2 times 10 to the minus 19 coulombs. You will likely remember that number because we use it so many times in this unit. But if you don't, now you know where to find it. Okay? Look on the right-hand side, plus 1e, or minus 1e, and then go to the left-hand side to remind yourself what an E stands for, the elementary charge. What about this notation now? This is what I call here. Ion notation. So if we have aluminum, 3+, that means we have an aluminum ion. It means the aluminum atom has become charged. How does it become charged? Well, it either gains or loses electrons in order to become charged. This notation, this thing that I call ion notation, tells us how much charge it has gained or lost. What do you think this means, 3+? Yep, Parker? Yeah, it's lost 3 electrons. Good. We know it's 3 because it's 3+. How do you know that it's lost electrons versus gained electrons? Yeah, good, exactly. If it's become positive, and it has, then it must have lost negative to become positive. So the charge of this aluminum would be 3 plus 3 times the elementary charge, which gives us 4.8 times 10 to the minus 19 coulombs. This second one, sodium, is similar to that. The charge of this is plus 1. If you don't see a number beside it, it just means 1 plus 1 times the elementary charge. Or the charge of this sodium ion would be just plus 1.60 times 10 to the minus 19 coulombs. Now the oxygen is a little bit different because it's 2-. It's a negatively charged ion. It must mean it has gained or lost. Parker, gained or lost electrons? The oxygen? It's gained electrons, right? It's become negative because it's gained negatives. The charge of that would be -2 times the elementary charge, -2 times 1.60 times 10 to the minus 19 coulombs, or we're going to make that -3.20 times 10 to the minus 19 coulombs. It's not a physics thing per se, but sometimes we see ion notation in questions, and we have to be able to identify what the charge of that ion is as part of a bigger question. Let's take a look at the first example that's in the booklet that I handed earlier. Example number 1 says a balloon is rubbed against hair, gaining a charge of -9.60 times 10 to the -9 coulombs. By the way, the unit for coulomb is the standard unit, but we often see NC, that stands for nanocoulomb, 10 to the minus 9 coulombs. We often see it written that way because a coulomb is such a big unit that we don't usually have a full coulomb of charge. So we often see it written as a nanocoulomb, 10 to the minus 9, or a microcoulomb, which is 10 to the minus 6 coulombs. Here they give it to me in coulombs, but they could have easily said -9.6 nanocoulombs, and you would have had to convert that, right? How many electrons has the balloon gained or lost? Firstly, Parker's going to answer this question because I know he knows it. Is it gained or lost, Parker? The negative balloon, has it gained electrons or lost electrons? Good. It's gained electrons because it's become negative. If it had lost electrons, then it would have become either less negative than it was or positive if it was neutral before. Okay, so it's definitely gained. Now, how many? Yeah. It would be, I believe it is 6, actually. How'd you figure that out?
I divided it by 1.6.
Yeah, yeah. Let me give you an analogy to help you to understand why we did what we did for that question, dividing this by that. If you go to Safeway and you weigh an orange and find it to be 200 grams, assuming all oranges have the same mass, then you get a bag, one of those plastic bags, and you fill it up with oranges. You're not sure how many you have because you didn't count. You weigh it. It weighs 1,200 grams. One orange, 200 grams. The bag of oranges is 1,200 grams. How many oranges do you have? 6. And how do you know that? Well, because you divided the total mass by the mass of one orange, right? And everybody can do that. Okay, everybody can do that question. The number of oranges is the total mass divided by the mass of one orange. You don't need to write that down, by the way. So how are we going to find the number of electrons, Matteo? The number of electrons will be not the total mass by the mass of one orange, but rather the total charge divided by, divided by the charge of one electron, right? So total mass divided by the mass of one, or in this case, the total charge divided by the charge of one. So we're going to say, just as Matteo said, -9.60 times 10 to the minus 9 coulombs, and we're going to divide that by -1.60 times 10 to the minus 9 coulombs, and that's going to give us exactly 6.00 electrons. Make sure you internalize this, okay? You're going to have to do this again, I promise you. You're going to have to do this again, find the number of electrons. And as the year goes on, you're going to have to find the number of a couple other things as well. One of the things you have to find in your EMR unit is the number of photons, whatever that is, the number of photons. The number of photons, you're going to say it's the total energy divided by the energy of one photon. It's always total divided by the amount for one. Okay, regardless of what you're dividing, it's always total by the amount for one. Yeah, question? Should be 19. Yeah, this should be 10 to the minus 19. So that actually should give me not 6. You're right. Thank you. That should be 6 times 10 to the, I think it's 10 to the 10. Yeah, 10 to the 10 electrons. Thank you. So total divided by the amount for one, whether it's total number of oranges divided by the mass, the total mass of oranges divided by the mass of one orange, the total charge of electrons divided by the charge of one electron, the total energy divided by the energy of one photon, whatever. It's always total divided by the amount for one when you're looking for a number. Here's our picture again, picture of the atom again. These were, remember, the protons and the neutrons in the nucleus. The neutrons don't really matter to us. The protons do sometimes. The electrons are orbiting around the nucleus. If we're going to transfer something, we alluded to this earlier on a couple of times. If we're going to transfer something, something's going to move from one to the other, from the balloon to my hair or from my hair to the balloon. What's it going to be? Protons or electrons? Yeah. Why is it going to be electrons, Nick? Tough one, hey? It's one of those things that, like, intuitively, lots of us know the answer to, but we don't necessarily know why. Okay, you're right. If you change the number of protons, you change the elements. So carbon has 6 protons. If it had 7 protons, it would be nitrogen. And that can actually happen, not under chemical means or not under electrical means, but under a nuclear phenomenon, that can actually happen. But that's not what we're talking about here. Okay, that's not nearly as easy to happen as an electrical interaction like we're talking about here. Electrically, if we have something moving, it's going to be electrons. Why though? Like, we know the effect if we move protons, but why is it that protons don't move? Like, why isn't it? Why doesn't it happen when you rub the balloon against your hair that protons move and it, sure, it changes the atom, right? But why doesn't it move and change the atom? Why does it have to be electrons? These electrons are held in place. They're held in orbit around the nucleus by, anybody know what kind of force it would be? It would be held in place by starts with a C, a centripetal force. Remember that from Physics 20? What's a centripetal force? A force that acts toward the center of a circle, yeah? A centripetal force. Centripetal force, though, you might remember, is always caused by something else. In this case, it's caused by electricity, an electrical force. There's an electrical force pulling this electron in toward the center, which causes it to orbit around the nucleus. There's also what we call a strong nuclear force that you're going to learn a lot more about in our last unit, Unit 5 of Physics 30. That's what holds the protons and neutrons in place inside the nucleus. That strong nuclear force isn't always bigger than electrical forces. But when you're talking about these distances, that strong nuclear force is bigger. So in other words, this electric force that holds it in orbit around does a pretty good job. But it doesn't do as good of a job as that strong nuclear force that's keeping the protons and neutrons together. So when you rub the balloon against your hair, you're not going to break the strong nuclear force. If anything, you're going to break the electric force bonds. And that's going to allow the electrons that were held in place by the electric force to start moving around, start moving somewhere else. So if something's going to move, under normal circumstances, it's going to be the electrons. Okay? Protons, as we said, can move, can leave the atom or change into something else. Okay, but that's a nuclear phenomenon, and that's a whole other unit, a whole other ballgame that's taking place. If something's going to move, remember that it's going to be electrons. Now, let's talk about how well electrons can move. Define 2 terms. We got a conductor and we've got an insulator. You guys have all heard these before and have some kind of notion as to what a conductor and an insulator is. Who thinks they can define it even loosely for me? Like, when you think of a conductor, what does it mean to you? Controlling? Okay, like the conductor of a train? Controlling a train? Say? Allows the electricity to travel. And we just said that the electricity, when it travels, is actually electrons that travel, right? Because it's the electrons that aren't as tightly bound to the nucleus, okay? So it's a material that allows electrons to travel. Yeah? Anybody want to add anything to that? That's a pretty good definition. It's a material that allows electrons to travel. Why does it allow electrons to travel, though? Well, because the electrons in the outermost regions of those atoms aren't as tightly bound to the nucleus. They're more free to move. Now, can anybody tell me, especially if you've taken chemistry, can anybody tell me what types of materials generally have electrons in their outermost regions that are freer to move? Copper is an example of one, yeah. Metals, yeah. We're talking about metals usually, right? Copper is a great conductor, yes. Aluminum is a good conductor, a very good conductor as well. Silver is a fantastic conductor. We don't wire our houses with silver, though, even though it's a better conductor than copper is, because silver is so expensive, right? Although copper is getting very expensive now as well. But we used to wire houses with aluminum. We don't do that anymore, even though aluminum is a really good conductor. Aluminum had this nasty problem of arcing. You know what that means? Electrons will jump from one to the other, from one wire to the other. And when electrons inside your wall jump from one wire to another, that tends to sparks, right? Tends to create sparks, which tends to create fire, right? So your house burns down. So aluminum wire is actually banned now. You're not allowed to use it to wire your house. Now we use solely copper to wire our houses. Even though aluminum is a really good conductor, almost as good as copper is. What's an insulator? Yeah, something that doesn't allow electrons to go, not very well anyways. Hey, there's nothing that would completely prevent electrons from going. Hey, there's nothing that's a perfect insulator, but generally the category of insulators we say are things that generally prevent electrons from flowing too well. That's because the electrons are more tightly bound than they are in the conductor. They're not as free to move around within the substance. Give me an example of an insulator. Rubber is a good insulator, yeah. Another one? Okay, yeah, that works. Wood is a good insulator. Glass is a good insulator. Plastic is a good insulator. Basically, we're talking about non-metals usually, right? Effective. This next page just shows various materials and where they rate relative to other materials in terms of conductivity. You can see that these guys, their relative conductivity is very, very high compared to these guys. Okay, you say that silver is 10 to the 8. Okay, that doesn't mean it has there's any units with that. It just means it's about 10 to the 18 times better of a conductor than wood is. And you can see, what's the commonality up here? These are metals. These are non-metals, right? So conductors are generally going to be metals, and insulators are generally going to be non-metals. All right, 3 laws of electric charge. Not much else to do here, guys. 3 laws. Then we'll talk about one other law that doesn't really fit within the same category as 3 laws. Do a couple questions. That's going to be pretty much it for us. I'm going to give you the first of these laws, and then I'm going to ask you what the other ones are. Once you know kind of the context of what I'm talking about, I think you'll be able to give them to me. First one, we say opposite charges attract each other. What does that mean? Well, charges that are not the same type, like in other words, one is positive, one is negative, they'll be pulled towards each other. They'll attract each other. What do you think the second law is? If opposite charges attract,
Same charges don't attract.
okay, same charges don't attract. We usually say that as like charges repel, but it means the same thing, yeah. Like charges repel each other. Positive pushes away positive. Negative pushes away negative. So we've talked about positive attracting negative, negative attracting positive, positive repelling positive, negative repelling negative. What have we not talked about yet? What have we missed? No? No. What about neutral? What about neutral things? Neutral things are attracted to charged things. Now this word here, objects, is important. Protons and neutrons are in the nucleus of all atoms. Protons and neutrons do not attract each other electrically, even though protons are positive and neutrons are neutral. Electrons and neutrons do not attract each other electrically, even though electrons are negative and neutrons are neutral. you need a neutral object. A charged balloon will attract a neutral wall, but a charged balloon won't attract a neutron. You're going to learn why that's the case tomorrow. Today, you're just going to have to trust me on that, but you do need the neutral object, not just neutral. You need a neutral object, the balloon, the wall, as opposed to the neutron, the small neutral particle. And the fourth law, again, that doesn't really fit within this. It's called the law of conservation of charge. Take you back to the law of conservation of energy for a second from Physics 20. Instead, energy can't be created or destroyed. It can be transferred from one to another, but it can't be created or destroyed. The law of conservation of momentum, we just went through that for the whole last unit. Total momentum remains the same, or in other words, momentum can't be created or destroyed. The law of conservation of X says X can't be created or destroyed. The law of conservation of charge says charge can't be created or destroyed. You can move it around. Like electrons can move from one object to the other and change the charge of individual objects. But if you look at the whole system, then the total charge has got to remain the same. All right, I want to finish class off today with 2 examples, and then that's it for us. You can close your books up after that. First example number 2 that's on your sheet, says 2 charged objects of similar size, similar shape, similar material momentarily touch each other. The first object initially had a charge of 2 times 10 to the minus 6. The second one is negative 3 times 10 to the minus 6. What's the final charge on both objects? Which one gained electrons and which object lost electrons? Well, let me tell you this. When 2 objects that are charged touch each other, they want to balance out. Now, I use that term loosely. That's personification, right, in English class. They don't really want to do anything, but we'll say they want to balance out. So whatever charge they have, we want to redistribute it so that the charge is balanced between the 2. That doesn't always happen. It happens, however, if the objects are similar size, shape, and material. If you have one object that's a conductor and one object that's an insulator, they won't necessarily balance out. If you have one object that's small and one object that's really, really big, they won't necessarily balance out. But if they're objects like this that are almost the same, then they're going to balance out. Any question that we see typically involves objects that are close enough to being the same that they will balance out. It's specified in this question, though, just so you know. Now, how do you figure out what the total charge is or the final charge is on both of these objects if they balance out? What is minus 3 and plus 2 going to balance out to be? No? You're not that far off, though. You said, okay, you're getting close. You said 2.5, which you were failing to take into account the negative there, right? Okay, now you're saying negative 1. You're almost there. Almost there. Anybody else? Negative 0.5 times 10 to the minus 6. Where does the 0.5 come from, Janae? Yes. Remember, we got to spread it out among 2 different charges, right? The total charge here is minus 1 times 10 to the minus 6. But that minus 1 times 10 to the minus 6 is distributed over 2 different charges. So each one of them is going to experience negative 0.5 times 10 to the minus 6. What we're going to do is average these out, basically. 2 times 10 to the minus 6 plus negative 3 times 10 to the minus 6 divided by 2 gives us 5.0 times 10 to the minus 7 coulombs. The total charge was minus 1 times 10 to the minus 6. If I add this up, this should have been negative 0.5, right? Negative 5. If we add this up, negative 5 times 10 to the minus 7 plus, well, the second one also has negative 5. It's going to add up to be negative 1 times 10 to the minus 6. So the total charge has remained the same. That make sense?
So what's the answer?
Yeah, both of them are -5 times 10 to the minus 7. We average them out. That's all we do. Now, which one's gained electrons? The 2 or the -3? Which one has gained electrons and which one has lost? Which one? The 2 has gained? Yeah. If the 2 was positive and it became negative, which it did, then it must have gained electrons. The -3 was negative. It became less negative, so it must have lost electrons. One of them loses, one of them gains. The one that becomes less negative has lost. The one that becomes more negative has gained. So let's say that this one has gained electrons right here, and let's say that this one has lost electrons right here. Okay, finally, last one for the day here. This one's tougher. It says ball number 1 initially has a charge of +3 coulombs. Ball number 1 touches ball number 2, which is a charge of -1. These are both big charges, right? That's okay. We can deal with that. It's not normal to have charges that are that large. Usually we're 10 to the -6, 10 to the -9, but that's fine. Ball number 1 and ball number 2 are separated. Then 1 touches 3, which is a charge of -5. What's the final charge on all 3 of them, assuming that they're similar size, similar shape, similar material? In other words, so that they balance out. What do? Add them up, divide by 3?
Yeah.
No. Yeah. Good recovery there. No, we don't do that, right? They don't touch each other at the same time. If they did, if they all touched each other at the same time, then yeah, we would add them up and divide by 3. But they touch them separately. So what we're going to do here is create a little table. We're going to say this is column number 1, column number 2, column number 3. Ball number 1 initially has a charge of +3 coulombs. Ball number 2 has a charge of -1 coulomb. And ball number 3 has a charge of -5 coulombs. The total charge here between the 3 different charges is going to be, what is that, -3? -3, Jacob? Yep. Total charge is -3. Now that -3 number has to stay the same always because of the law of conservation of charge. But when ball number 1 and ball number 2 touch each other, those two will balance out. What do they balance out to be? Okay? They're going to be 1. Yeah, +1. Why? Well, because 3 plus -1 is 2. Divided by 2 is 1. Average them out. +1 and +1. Now, this one hasn't changed because we haven't touched object number 3 yet, so it's still -5 coulombs. Let's add these up just to make sure that we've got the same total charge, which we should. 1 and 1 and -5 is -3. Seems like we've done it right so far because we've maintained the same total charge. Now it says ball 1 and 2 are separated, then 1 touches 3. 1 touches 3 now. Now 1 and 3 are going to balance out, and they're going to balance out to be what? -2 and -2. 1 plus -5 is -4. Divide that by 2 gives me -2. Average them out, you're going to get -2 and -2. Ball number 2 remains the same because we haven't touched it this time. Let's add these up just to make sure we have the same total charge of -3. -2 plus 1 minus 2 gives me -3. Sure enough, looks like we've done it correct. The final charge on all 3 of them is -2 coulombs, +1 coulombs, and -2 coulombs. Now, if I asked you what physics principle you used to answer question number 3 or question number 2, which physics principle listed in the bottom left-hand corner of your data sheet or at the back of the room would you have used? No. Principle 7, conservation of charge. Conservation of charge we apply in a number of different situations this year. The first of them is today, where you can see that I've written down at the back there, if we touch charges and they balance, that's conservation of charge.